Okay, so we're going to spend the last couple lessons looking at max and min problems. Remember that Tuesday we'll have a quiz on this chapter. We'll also be starting the next chapter on curve sketching. So, as we've been saying, the stuff that we've looked at so far, for the most part, especially intervals of increase and decrease, as well as max and min values, will lead us directly into sketching some curves. And we'll be learning a few more tricks for sketching curves and using those as well as what you learned in 30-1 to help us sketch pretty much any type of function. We'll spend the last couple days looking at max and min problems. In 20-1, you did some work with max and mins of quadratic functions. You found the vertex a couple different ways. One of those ways was converting from uh, standard form or to vertex form, a bracket x minus p all squared plus q. So that was one of the things that you did in 20-1 to find where the max and or min of a quadratic function was. But now we can use derivatives for that. So if we have any type of function, we can find the max or min of that function by taking the derivative and finding where the derivative equals 0. Because as we've seen, the derivative gives you the slope of the tangent. And at a max or min point, the tangent line will be horizontal. Its slope will be 0. So the derivative will equal 0. So let's first example, find two positive numbers whose product is 10,000 and whose sum is a minimum. So we need to start these by setting up some variables. Our equations can only have one variable in them. So if we start with the letter x, we'll let x equal the first number. And initially, let's say that y is the second number, but we can't keep that variable y because our equation can only involve one variable. But we do know that the product of the two numbers is 10,000 and the sum is a minimum. So because we're told the sum is a minimum, we need to come up with an expression for the sum of these two numbers in terms of a single variable, and that's what we're going to differentiate. The fact that the product is 10,000 allows us to write the second variable in terms of the first. Because their product is 10,000, that means x times y is 10,000. So y, the second number in terms of the first, can be found by dividing both sides by x. Or saying that y equals 10,000 x to the negative 1. Now we have expressions for both numbers in terms of the single variable. And again, we want to minimize the sum. So s, the sum, an expression for that would be x plus 10,000 x to the negative 1. And now we're going to differentiate. So ds by dx will equal 1 minus 10,000 x to the negative 2, which we will make equal 0. And at this point, there's a couple different things that we could do. We could add that 10,000 x to the negative 2 to both sides. So 1 would equal 10,000. I got one too many zeros there. X to the negative 2, or 1 equals 10,000 over x squared. And then if you cross multiply, x squared will equal 10,000. And x would equal, now normally we would say there would be two roots, the positive and the negative, but we're asked to find two positive numbers. So we'll just take the positive root of 10,000, which is 100. So there's the first number. X is 100. And the second number, y, is found by going 10,000 over x, or 10,000 over 100, which is also 100. So there's lots of different numbers whose product is 10,000. We want to find the two numbers whose sum is a minimum. And we see now that that occurs when both numbers are 100. Okay, so again, there's lots of different numbers that will multiply to get 10,000. For example, 5,000 times 2 is 10,000. But if you add those two together, you'll get 5,002, which is a much larger number than you get when you add the 100 and the 100 together. That is only a sum of 200. Okay, so 1,000 times 10 also multiplies to get 10,000. But if you add those together, you'll get 1,010. Again, that's a much larger sum than when you add 100 and 100 together. Right, so using derivatives, we can find the answer to this, and we can say that the two numbers are 100 and 100. Number 2, rectangular dog run is to be fenced off using the side of a garage as one of its boundaries. They only have 120 feet of fencing available. Determine the dimensions that will maximize the area of the dog run. So this is a very practical problem. Right? They've only got so much of this fencing to use, and obviously they want the largest possible area for the dog to run in. So we need to come up with an expression for area involving one variable only, and that's what we will differentiate because we want to maximize the area. So if we just draw a bit of a diagram here, right, the side of the garage is used as one of the boundaries of the dog run, which means there's only going to be 3 sides of fencing. So if we say that W is the width and L is the length, let's start again by identifying that W is the width. And we need to come up with an expression for the length in terms of the variable W. And the length, because we have 120 feet of fencing, if you take off the 2 W's from whatever, or from the 120, whatever's left is going to be what's left for the length. So the length would be 120 minus 2W. And now we have an expression for both the width and length in terms of the same variable W. And because we want to maximize area, we need to have an expression for area, which is length times width, or width times length. So in this case here, that'll be negative 2W squared plus 120W. So there's our expression that we're going to differentiate. So dA by dW will be negative 4W plus 120. And again, the maximum will occur when that equals 0. So if you add the 4W to both sides and then divide by 4, W will equal 30, and that would be in feet. And then the length, L, is 120 minus 2W. 120 minus 60 is 60 feet. So there's the dimensions that will maximize the area. That would be an area of 1,800 square feet. Obviously, there's lots of different dimensions that could be written down here using 120 feet of fencing. For example, let's say that W was 10, so that would be 10 on the left side, 10 on the right side. That's 20 feet. You'd have 100 feet left over for the length, but 10 times 100 is only 1,000. Right? At 30 times 60, we're at 1,800 square feet, much bigger, much larger area. So again, you could take any different values for W that you wanted and then determine what L would be for that value of W. And if you find the area, it will always be less than the 1,800 that we got in our problem. Now, something you might be wondering, well, the last one said, what are the two numbers so that the sum is a minimum? In this case, what is the area so that, or what are the dimensions so that the area is a maximum? These problems are always set up that if it asks you for the min or the max, the number you get will correspond to either the min or the max. But you can also confirm that by using something that we have been doing, and that is if you take your critical number here, the zero of the derivative was 30, and if you see what the value of the derivative is on either side of 30, so for example, you could let W equal 0, because that's to the left of 30, and the derivative would be negative 4 times 0, which is 0 plus 120. That's a positive value. Okay, a number to the right of 30, let's say 40. Well, negative 4 times 40 is negative 160, plus 120 is negative 40. So this confirms that for any number to the left of 30, the derivative is positive, or the graph of the derivative would be increasing in value. And to the right of 30, it's negative, or the graph of the derivative is decreasing. So that confirms that there'll be a maximum at 30. Okay? But again, the problems are always set up for the most part where if it says that you're looking for the maximum, the answer you get will give you the maximum. And same thing if you're asked for the minimum. Number 3, rectangular box is constructed from a 16 centimeter by 6 centimeter piece of tin. Equal size squares are cut from the four corners. The edges are turned up to form the box. Determine the dimensions of the box that would maximize and minimize the volume. So in this case here, you're starting with a 16 by 6 piece of tin. And then you've got equal squares being cut out of each corner. And then once those squares are cut out, the edges are turned up, and that's where the box comes from. So we can let x by x be the dimensions of those equal squares that are cut out. So originally the box was the piece of tin was 16 by 6 centimeters. So once those, again, squares are cut out and the edges are turned up, that's going to make the length and width smaller than 6 and 16. It's going to make them smaller by 2x's because that's what you're taking off the length and the width. So the length of the box would be 16 minus 2x, and the width would be 6 minus 2x. And the box would have a height of x. Again, those corners are cut out and then the edges are turned up, and so the box will have a height of x. We want to determine the dimensions that would maximize and minimize the volume. And the volume of a box is length times width times height. It doesn't matter what order you do these in. I'm going to put the height first, times the length and the width. So that gives us 16x minus 2x squared times 6 minus 2x. 6 times 16 is 96x. The outer products would be negative 32x squared. The inner products would be negative 12 x squared, and the last would be positive 4x cubed. So if we simplify, it'll be 4x cubed minus 44x squared plus 96x. There's an expression for volume. And we want to both maximize and minimize that, so we need to differentiate. The derivative would be 12x squared minus 88x plus 96. Which we want to find a zero of that. Now, there is a common factor here of 4, I think. This leaves us with 3x squared minus 22x plus 24. And then that quadratic can be factored, and it's going to give us two critical numbers. And one of those will be where we'll have a maximum volume, the other will be where we have a minimum volume. So the front terms multiply to get 3x squared, so 3x and x. The last terms have to multiply to get positive 24, and when we multiply out the binomials, the outside and the inside products will have to combine to get negative 22x. So it'll work if you have a minus 4 with the 3x and a minus 6 with the x. The outer product is negative 18x, the inner product is negative 4x. That gives you your negative 22x. So our solutions will come where each factor equals 0. And so there's our two critical numbers. However, 6 won't work. 6 won't work because the original width of the piece of tin is 6 centimeters. And if x equals 6, then the width will be negative 6. 6 take away 2x. So 6 is an extraneous root. So that leaves us with only one critical number to look at, and that's x equals 4/3. So if we put that on our number line, because we need to find a max and a min, and we choose a number to the left of 4/3, a number like 1, and I'm going to go back and use the factored form of the derivative. The first factor is positive 4, so that's a constant. When x equals 1, the second factor will be negative, and the third factor will be negative. 2 negative times a positive is a positive, so the function is increasing in that interval. To the right of 4/3, a number like 2. Again, the first factor is a constant, positive 4. When x is 2, 3 times 2 is 6. Take away 4 is positive 2. And for the third factor, when x is 2, you're going to get negative 4. So what this tells us is that the maximum volume will be when x equals 4/3. And remember, x refers to the dimensions of the corners that are cut out, the equal size squares that are cut out of each corner to form that box. And so if that's our maximum volume, our minimum would occur when x equals 0. In other words, you have no box, which should make sense. Right? So maximum volume occurs when x equals 4/3 of a centimeter, and the minimum volume will be at x equals 0. In other words, you don't have a box at all. So you got a volume of 0. So this one's a little bit different. Box is to be constructed so that its volume is 1,000 cubic centimeters. The top and bottom of the box are to be square while the sides are rectangular. Determine the dimensions of the box that will require the least amount of material. In other words, you want to minimize the surface area. So again, this is a practical problem, right? Because obviously, the more material it takes to construct a container, the more it costs the company to produce their product. So they want to minimize their costs. So in this case, they want to minimize the surface area, the amount of material that is used to construct the box. So we're told that the box is made of a square top and bottom, and then the sides are rectangular. So we can draw a picture of what that might look like. And again, the top and bottom are squares, and maybe we'll say h represents the height. And because we want to minimize the surface area, we need to come up with an expression for the surface area in terms of one variable, and that's what we will differentiate. But again, it can only be in terms of one variable. So this is where the fact that the volume is 1,000 centimeters cubed comes from. We can write h, the height, in terms of x, because the volume, which will be x times x, which is x squared, times h, is 1,000. So h then is 1,000 over x squared. Or 1,000 x to the negative 2. And now we have an expression for h in terms of x. Again, we want to minimize the surface area. So the surface area of this box. So that'll be the top and the bottom, which measure x by x. The area of the top and the bottom would be 2x squared together, plus 4 sides that measure x by h. But h is 1,000 x to the negative 2. So when you multiply these out, it'll be 2x squared plus 4,000 x to the negative 1. Because you're going to multiply the x to the 1 by x to the negative 2. So there's an expression for surface area. And that's what we're going to differentiate. So dSA over dx will equal 4x minus 4,000 x to the negative 2. And we want to know where that equals 0. Now we had one similar to this before where we were able just to solve for x, and I think we can do the same thing here. We have another option though. We could write this as a rational expression, move the x to the negative 2 down to the bottom, get a common denominator, and then solve it that way. So let's do it that way first. So 4x minus 4,000 over x squared equals 0. Our common denominator would be x squared, so we'd multiply top and bottom of that first term by x squared, which would give us 4x cubed. Minus 4,000 all over x squared equals 0. And a rational function equals 0 when the numerator equals 0. So that'll be where 4x cubed minus 4,000 equals 0. And then we can solve for x by adding the 4,000 to both sides, dividing by 4. So x cubed will equal 1,000. And then taking the cube root of both sides, and x will equal 10. And that'll be 10 centimeters. So x, remember, are the dimensions of the square top and bottom. So that's 10 by 10. And then h is 1,000 over x squared, or 1,000 over 10 squared, which is 1,000 over 100, which is also 10. So it turns out that the minimum surface area occurs when the box is actually a cube, where the length, width, and height are all the same. So, as I said, one way that you could solve for the derivative, which is what we did right here, is by getting a common denominator, writing it as a rational expression, and then saying that a rational expression equals 0 when the numerator equals 0. But we also could have done this by factoring. You have a common factor here of 4x to the negative 2. Right? Both terms are divisible by 4, and remember, when you're looking for the common factor of x, you take out the one that has the smallest power. So when you divide 4x by 4x to the negative 2, the 4's cancel, and you'll have x to the 1 divided by x to the negative 2. That's done by subtracting the exponents. 1 take away negative 2 becomes 1 plus 2, which is 3, minus, and when you divide 4,000 by 4, you're going to get 1,000. And when you divide the x squareds, they cancel. So our solutions come where each factor equals 0. And for the first factor, that would be where x is 0, which is not permissible because you no longer have a box. If x is 0, you don't have a length and you don't have a base at all, which obviously won't work. The second factor, though, x cubed minus 1,000 equals 0, solution to that would be when x cubed equals 1,000, and then you take the cube root and you get your 10 centimeters that way as well. So either way works. You get a common denominator, express the derivative as a rational function, and then a rational function equals 0 when the numerator equals 0. Or you can simply factor. Okay, this one's going to be a little different. We've seen one similar to it, but we're going to see as we go through it that it's going to have a slightly different twist to it. So again, you're starting with a piece of cardboard measuring 18 by 4. You cut out those equal squares from the four corners. Edges are turned up to form the box. Determine the dimensions that would maximize, and also what is that maximum volume. So I don't think we have to draw a diagram for this one because it's the same as the previous one we did. The volume will be the height, which will be x. If you say that the equal squares that are cut out of the corners are x by x. So the length would be 18 minus 2x, and the width would be 4 minus 2x. So if you multiply out these three factors, you're going to get 4x cubed minus 44x squared plus 72x. If you multiply out those three factors. And then the derivative, dv by dx, will be 12x squared minus 88x plus 72. And again, we want to know where that equals 0. So again, there is a common factor here, a common factor of 4. But the issue now is that that quadratic that's inside the brackets actually cannot be factored. But that's okay because we always have the quadratic formula, which remember is x equals negative b plus or minus the root of b squared minus 4ac all over 2a. So negative b will be positive 22 plus or minus the root of b, which is negative 22 all squared minus 4 times a times c all over 2 times a. So if we determine the value of the discriminant, negative 22 all squared minus 4 times a times c gives us a discriminant of 268. And that can be reduced, but 268 is not a perfect square. I'm pretty sure it's divisible by 4. Yeah, so root 4, root 67. And the square root of 4 is 2. And then you could divide all three terms by 2. And that would be the exact value of the critical numbers, right, where the derivative equals 0. So we're going to have to convert them to decimal. 11 plus the root of 67, all in brackets, all divided by 3. So approximately 6.4 is one critical number. And then the other one will be where it's 11 minus the root of 67 all over 3. 0.94. And once again, the 6.4 will be extraneous, because if x is 6.4, the last factor is going to be negative. We can't have a negative dimension. So that is an extraneous critical number. The only one that we can look at is 0.94. And again, we can confirm that we're going to get a maximum volume at x equals 0.94. Obviously, it can't be less than 0. So when we say we're going to take a number to the left of 0.94, it can't be negative, because that would give us a negative dimension. But we could use a value like, let's say, 0.5. So let me store this number into memory, because I think we're going to need it. And now when x equals 0.5, and I plug that value into the derivative, so 3 times 0.5 squared minus 22 times 0.5 plus 18 is a positive value. To the right of 0.94, a number like positive 1, it's going to be 3 take away 22, which is negative 19, plus 18 is negative 1. So that confirms that you're going to have a maximum when x equals 0.94. .94 centimeters. And we can find out what that maximum volume is by taking my answer of 0.94 and plug it into my volume formula. So this is why I saved that number into memory slot A. Our volume is 4 times x, which again, try that again. I put in memory slot A, and that number is cubed, minus 44 times A all squared plus 72A. So there's our maximum volume, approximately 32.12 cubic centimeters. .12 centimeters cubed is our maximum volume. So you can do questions 1 through 3 and 5 through 8 on page 188 and 189. I will post those solutions to Google Classroom. You can check your answers. We'll spend one more day looking at these on Monday, and then Tuesday we'll start curve sketching, and you guys will write your quiz on extreme values.